So we've been working with Holger now for quite a while. He's a principal FL scientist at NVIDIA. As you would have seen, he attended the FLARE AI Summit last year and demonstrated an early prototype of FLARE and NVIDIA FLARE interoperability. And so today he's going to give us an update as to how it's been going, how far we've gotten in this collaboration. And so with that, we're just getting it set up and we're ready to go. So thank you, Holger.
Okay.
Thank you.
Thanks, Nick. Thanks for having me here. It's very exciting to see all the growing community of Federated Learning researchers and practitioners coming together here. So thanks for having me. And as Nick was saying, we've been working together for the last year, mostly on the interoperability, getting FLARE algorithms working in FLARE. And today I would like to talk to you a little bit about how you could use NVIDIA FLARE to protect the model IP of your FLARE models if you are deploying them. Okay, so just for people who might not know, NVIDIA FLARE has been around as an open source federated learning framework for a couple of years now. We try to be industry agnostic, so we have applications going from healthcare to financial services, pharmaceutical, energy, autonomous driving. We historically focused on the so-called cross-silo or cross-enterprise applications. So you're thinking of connecting different hospitals, banks, financial services. With the latest release, we are also supporting now cross-device applications of federated learning. So if you want to have a very scalable deployment for supporting millions of devices, only last week at GTC, the NVIDIA GPU Technology Conference, we demoed a use case where we use PyTorch Executorch on a mobile phone for training models in a federated scenario. So of course, for having a production-ready system, we've been early on focusing on things like user identification, data encryption in transit, potential for site policy measurements that each data owner can enforce, and then different sets of privacy-preserving algorithms, going from differential privacy to homomorphic encryption. And today I want to focus a little bit on the hardware-based solutions on confidential computing. Just to summarize again, FLARE is open source. We have integration with FLARE and other libraries. Maybe some of the highlights are it's pretty easy to convert your standardized training code to a FLARE federated learning deployment. So we focused a lot on making it easy with a few lines of code changes to get your standalone training algorithm running in a federated scenario. We have support for large language model streaming. If you want to support billions of parameters, several gigabytes of messages, you can do that using FLARE. We've been used by many companies and research institutions over the years, and have been closely working with the FLARE team on the integration. So basically, as of currently, you can take a FLARE server app and client app and run them in a FLARE deployment, which is very beneficial for our users, right? You can imagine there are several customers who are using FLARE in production at the moment, and they want to utilize the nice FLARE ecosystem of algorithms and new strategies that have been developed by the community. So in this way, we can benefit from each other and build up the federated learning ecosystem as a whole. But federated learning has a couple of risks that I think most people are aware of. By design, it's not completely data preserving, so you need to, or privacy preserving, so you need to consider additional measurements in order to protect different points of your system, especially with regard to IP protection. Let's say I'm a model owner and I want to send my model to clients. but I not completely trust those clients that they might not copy out my model. And therefore, I'm under the risk of model IP theft. Right? This could be at the transmission side, it could be storage, it could be compromised machines on the server or the client side. So as a solution, NVIDIA provides a confidential compute environment, which is a hardware-based solution to encrypt data in use. And I thought it's maybe easiest if I show a little video that explains this. I hope the audio is going to work.
Volumes of sensitive data are being generated every day. But while traditional systems protect data at rest and in transit, data in use is left vulnerable. Now, with NVIDIA confidential computing, data and AI models can be secured while they're being used. This security feature in the NVIDIA Hopper architecture makes the NVIDIA H100.
Sorry, I should have told you. Maybe let me play it again. Not working?
I think it's any second now. No sound? No sound.
How to do this?
We're actually pretty close. This thing?
Massive volumes of sensitive data are being generated every day.
They start talking.
Sorry about that. Okay.
Massive volumes of sensitive data are being generated every day. While traditional systems protect data at rest and in transit, data in use is left vulnerable. Now, with NVIDIA confidential computing, data and AI models can be secured while they're being used. This security feature in the NVIDIA Hopper architecture makes the NVIDIA H100 Tensor Core GPU the world's first accelerator with confidential computing capabilities. The strong hardware-based security in Hopper guarantees full virtual machine isolation within infrastructure that's on premises, in the cloud, or at the edge. This prevents unauthorized entities, including the hypervisor, host operating system, infrastructure owner, or anyone with physical access, from viewing or changing code and data during execution. Protecting AI models in use is especially important for independent software vendors who develop industry-specific AI solutions. These ISVs distribute their AI models and solutions to customers spread across multiple locations, which puts their IP at risk from external attacks and internal threats. With NVIDIA confidential computing, ISVs, as well as enterprises in every industry, can deploy their data and AI models securely from edge to cloud. Massive volumes of sensitive data are being generated every day, but while traditional systems
solution in FLARE. This is, as the video mentioned, it's available since the Hopper architecture, and now future generations like Black will support it as well. There's a virtualization-based trusted execution environment, which I should highlight, which basically allows you to take code that works in a non-confidential compute environment and just run it in a confidential compute. So as a model or as a user, model developer, you don't need to consider any other, additional changes. We work together with the CPU, trusted execution environment providers, in order to have the whole system, coming from data I/O through the CPU to the GPU for training and efficient inference, make the whole system end-to-end secure. And this works together with the cloud providers and other station services to make sure that everyone is actually running the hardware they're claiming to run. So now with our Flower integration, it becomes really easy to make use of some of the features of both Flare and Flower. So in this example, we're using a Flower client and server together with some of the experiment tracking from Flare. So here we import a summary writer, and in the Flower, this is a standard NumPy client from Flower. In the fit routine, we add additional metric streaming capabilities that allows us to stream the training process to a MLflow server. So that server is the only port that's open in the confidential compute environment in order to write those metrics out. So we use a Python API to submit a job. In this case, it's a Flower PyTorch MLflow job. And then as a user, you will be able to see the training and validation metrics displayed as the training goes on. And this one is without sound, I hope. But it basically shows you that now on the server side, right, if you are concerned about a curious administrator and the cloud provider accessing the processes that are running on your server, we can basically ensure that this is not possible. So in Azure, we use a confidential virtual machine to run on the confidential compute environment, and all the SSH access is blocked, and you can basically not access the processes running here. Similar on the client side, we run a bare metal client in this case. Sorry, is this? On the client side, we run the bare metal client, which is basically kicking off the process, and then nobody can touch it. They will be able to kill it, but nobody can log in, and there's a check running here that shows no open ports are available for connecting to the site. So in the end, we build additional hardening around the confidential compute, which includes ongoing or continuous cross-verification, saying that you're running in attested machines. We restrict the network traffic, basically ensuring that only communication happens that is needed for the federated learning. We have the access lockdown that I just demoed, both on the server and the clients, and additional in-memory memory managed keys to make sure that all the results are stored in encrypted spaces as well. So you can think of this whole federated learning system becoming a black hole. Basically, nothing goes in and out apart from the data that is provided inside a confidential compute, and the result will only be downloadable by authorized users. And that way we drastically reduce the attack surface for federated learning, and think it becomes overall a more secure ecosystem. Okay, just a few announcements. We have our annual NVIDIA FLARE Day happening later this year. This time we're planning 2 days, one for the US and Europe, and one for Asia in September to showcase some of the different use cases of FLARE. If you're interested, last year the Flower team also presented, and you can look at the recording. We're looking actively for contributions. It's an open source framework, so if you're interested, reach out, try to commit your algorithms or examples even using Flower, for example, and you can get a chance to speak at one of our events. Also, what might be of interest is NVIDIA's academic grant program, which allows you, is looking for proposals for Edge AI. So you can get both cloud compute credits and hardware awards as part of your grant. Okay, with that, I'd like to thank you for your attention.
We'll take a couple of quick questions if they're out there. From the back. Mic is coming.
So what is the performance overhead of doing everything in the confidential computing, everything encrypted? So do you have some benchmarks, numbers on that?
Right. We did some experiments, and we saw about a 4% overhead for completing the whole training in a standard CNN training procedure, maybe 100 rounds communication. So it's pretty reasonable, I would say. And of course, if you compare it to like homomorphic encryption solutions, it's like 100 times speed ups, because you don't need to worry about encrypting the messages anymore.
Yeah, that's impressive. Thanks.
Anything else? Oh, yeah. We have Patrick from Intel.
So great talk, first of all. I love confidential compute. Excited to talk more about that. And the hardening, I think, is a great area to focus. Glad that you're positioning there. I wanted to understand how you're, so you said that you're locking down the network traffic. Can that be measured in some way? Tested, I guess, is the...
I mean, basically all ports that are not used for the FL communication are going to be locked down or blocked, right? So apart from that ML flow communication to that server. So there's like a lot of additional like concerns of, or like, let's say, configurations you need to make sure happen, right? So in order to deploy this, there are like certain steps where we're actually currently working on trying to simplify that for the most common use cases.
Excellent. Thanks.
Okay, great. Let's thank Holger again. Thank you.
Thank you.